Morning, everyone. So today we're going to continue with our overview summary. Today we're going to look at Chapter 8, which is on atomic theory. Remember, this was a chapter that was fairly long. It sort of jumps through a lot of different topics, but hopefully I can overview some of the higher level concepts with you. First part of this chapter here was mainly to look at the concept of the atom. Okay, now we know atom is a really tiny particle. Everything is made out of different atoms. Our understanding of the atom here has changed over the last maybe 200, 300 years or so. So for this first part here, you do need to know a little bit of the history here. For the picture of the atom, we started looking at a guy called John Dalton. Obviously, he based his work off of people before him, but we sort of credit him with this model here. Dalton's model here was known as the solid sphere model. Essentially, the idea here was everything is made out of these tiny particles. You take a sharp enough knife and you sort of chop it down. Eventually, you come to this really, really tiny particle. The root word here, atomos, actually means small. And he devised that there's nothing tinier than the atom. It's indivisible, it's indestructible here, and everything is made out of these building blocks. About 100 years afterwards, we had a fellow named J.J. Thomson. He was working with old TV sets, CRT sets, and he had devised, well, there have to be some things in the atom here that are actually charged, so actually he can actually deflect them using different electric fields, magnetic fields, things like that. So he had actually discovered electrons. For him, these electrons here had to be tinier than the atom, so we had a bunch of these negative charges here, but to keep consistent with what Dalton said previously here, he said these negatively charged plums were sitting in a background of a positive batter. So we just typically call his model here the plum pudding model. You may have heard here the raisin bun model. It's basically like little raisins or blueberries that are embedded inside a muffin worth of material. Still overall neutral, so that gives us this notion here. The number of positives has to cancel the number of negatives. But a decade after him, he had a guy, Rutherford, came along. Rutherford, he was most well known for his gold foil experiment. He shot alpha particles, which were fast-moving positive particles. He wanted to test whether Thomson's model was correct, where the negatives are just all over the place here. They're just sort of spread out randomly here. There's no sort of orientation or arrangement to them. Because he had found, although a lot of the alpha particles here did cut through, like he hypothesized, but some of them actually interacting on an incoming course here with the nucleus actually ended up reflecting back the way it came. He ended up devising more so like a planetary model. So his planetary model here had the atom still very tiny. We have the electrons sort of marking off the far reaches of the atom. But what he had discovered was most of this atom here was actually empty space. In fact, a lot of this batter material here could have been squeezed down into a tiny dense core. Nowadays we know of protons, and that made out the nucleus. Around the same time here, we had a fellow named Chadwick who had discovered neutrons. So that sort of fills up the remainder of the nucleus. So that as he shot these alpha particles in, if the alpha particles here were not on a collision course with the nucleus, being a positively charged particle here, it would encounter a little bit of deflection from the proton. If it was on a collision course here, it's not going to just sort of stop in its tracks right away. It takes a little while to actually lose its velocity, but by the time it slows down and comes to a stop, not really wanting to head towards a positive, it would actually end up deflecting back the way it came. So you use this to actually devise a sort of solar system, this planetary style model, which Bohr came along and just took and ran with it here. The electrons are definitely in these shells, these different orbits, but the electrons are not just in one single orbit. For Bohr, what ended up happening was he ended up having, let's say, our nucleus, but he had quantized shells. We usually use the letter N to identify which shell we're on. So let's say N equals 1, the first orbit here. The electrons have to be on certain steps, certain orbits going upwards from there. And for some reason, there was sort of some limit to these shells here. So if you remember here, our first shell being so close to the nucleus here could only hold 2 electrons. The second shell a little bit farther out here, we still fill them in here, single, 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 single. We only start pairing it by the time we get to the 5th one. We start going pair, 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 pair. That one maxes out at 8. And then similarly, the third shell going out from there, electrons having a negative charge, given a choice, they want to be as close to the positive as possible. If they didn't have any motion, they would actually just spiral into the nucleus. But because of this sort of, we call it a tangential velocity here, because it's sort of speeding along here, it is that sort of attraction to the core that keeps it in the circle here. The third shell out here, even though size-wise here is a lot farther out, it can also only handle 2. It can only handle 8. So we can actually get sort of a simplified Bohr model here. Let's say I have sodium. Sodium has 11 electrons, 2 on the inside, 8 on this outer shell here. It only has 1 out of the 8 spots filled up, so be it. So for sodium, as a simple, sometimes call it a simple Bohr model, or they even call it an electron arrangement. And that essentially is just looking from inside to out, how many electrons are on each of these floors. Well, we have 2 on the first floor, 8 on this floor. I know the maximum for the third shell is 8, but sodium doesn't have enough electrons to fill that up. So for sodium here, it would be 2, 8, 1. Sometimes 2.8.1. Basically, it's identifying for you on each of the orbits, on each of the shells, how many electrons are on each of these floors here. Bohr had did some studies here with excitation, absorbing, emission kind of spectra to sort of cement his understanding that these ones here were discrete and quantized. Just before we get to that there, we did look over a little bit, focusing here more so on the neutrons. Those neutral particles are the other heavy particle in the nucleus that makes up the molar mass. So let's take chlorine as an example here. Chlorine element 17. Our periodic table say 35.5 or 35.45 if you have a little more precise. This element number here is called its atomic number. The atomic number here, we're going to use capital Z for it. Capital Z actually identifies for us how many protons. The thing that makes chlorine chlorine is having 17 positives inside the center. The protons are heavy, they have a mass of 1 here. When we start looking at a molar mass here, hey, how come it's 0.5? We're actually not chopping up protons or chopping up neutrons. We saw previously that this was actually a weighted average of the forms of chlorine that actually exists. So doing more studies, we've actually found chlorine can either be the 35 isotope or chlorine can be the 37 isotope. No single chlorine atom actually weighs 35.45, but because these two versions of chlorine here come at a different proportion, when I do an average, the average doesn't put me just right in the middle, like let's say 36. The average is skewed towards the one that's more common. Looking at this one here, it turns out there's actually about 3 of the lighter isotope for every 1 heavier isotope. I'll just color that in so you can see the difference there. So the actual chlorines only weigh 35, they only weigh 37, but averaging it based on this, they call this sometimes a fractional abundance. So the abundance in our universe, they actually ends up being perhaps decimals here. Note we're not chopping any chlorines here, but given a handful, given a sample of chlorine here, given about 3/4 of them are the lighter type, and then 1/4 is the heavier type here, it's kind of like all 4 atoms weigh about 35.45 or 35.5, and this one here is known as a weighted average. It's a skewed average that's pushed towards the one that's more common. There is a formula for us to memorize here. This weighted average here is what our periodic table gives us. I'm just going to say PT. And essentially, we are going to factor in all these different versions, all these different isotopes. In this case here, there's 2 versions of it, mass 1 and mass 2. But again, what we're going to factor in is their percentage abundance, how common they are in the universe. So we're going to say, let's say %1 plus %2. If I have an example of an element that has more isotopes than this here, I just keep tacking on another mass, another percent term. So just doing a numerical example for us here, our periodic table here says 35.5, so that's already the weighted average. They already gave me that number. Being told that these are the only 2 versions of chlorine, one of them weighs 35, one of them weighs 37, we should be able to identify, is this 3/4 correct? And we can actually get it to a little bit more precise as well. When I do our percentage here, not knowing something here, I'm going to put an X to it. So that's going to be a fraction, that's going to be percent. It may worry you, oh no, I have 2 unknowns here, I only have 1 equation. But in this case here, being the only 2 versions that chlorine can exist in, we actually know there's a relationship between these 2 percentages. Whatever is not this is going to be the other one. If this were 20%, right away that's 80. If this is 60, right away that's 40. So seeing as we're doing math with percent here, I basically want to say out of the 100%, if I don't care about the X part, that was the lighter isotope here, I'd actually plop in here a 1 minus X instead. Okay, so it would have been a hard problem there. It actually just boils down to a little bit of algebra. Let me clean this up a little bit here. This is just going to be 35x. I would need to distribute the 37 in. So I'm going to multiply that. So I get 37 minus 37x. I'm going to collect up my like terms. So collect up all the terms that have x on the right-hand side. 35 minus 37 is going to be minus 2x. I'm going to drag this 37 over. I'm going to minus 37. So 35.5 minus 37 gives me negative 1.5. Sometimes people start pausing here and they're like, oh no, I have a percentage that's negative, whatnot. I haven't quite finished the math just yet here. I still need to divide both sides by negative 2, and doing that here gives me pretty spot on 0.75 means x. Even though it was a little bit of work, a little bit of math to actually get to this percentage here, always good to go back and actually reread the question, what we're looking for. Well, I just want to verify whether this abundance, a 3 to 1 sort of ratio here is actually correct. Well, good. X is actually what I have put for the percentage of the 35 isotope. So chlorine 35 comes to us about 75% of the time, whereas chlorine 37 actually comes to us 25% of the time. We're skewed slightly in favor of the lighter isotope. You might remember from previous years here, for us to get a sense of the neutrons, we would normally just round this number. I know I'm not chopping protons and neutrons here. Well, this number, when it's rounded, it's actually 36. You'll notice in this case here, it actually gets it wrong. There is no chlorine that actually weighs 36. But it does have the idea, because the average is skewed towards the one that's most common, well, it's kind of like chlorine weighs 35.5 or even 36 here, and that's actually where we just roughly just understand our neutron number, even though in our chlorine example it actually gets it wrong. If we know out of this 36, 17 of them are protons, I can just do a quick subtraction here. I know the 36 is actually wrong, but 36 minus 17, that's sort of like saying 19 neutrons if I just did a plain old rounding of that number there. When in reality, my chlorine sample here, I actually have only 18 neutrons for the 35 kind and 20 neutrons for the 37 kind. Okay. So just using that example just to verify fractional abundance for us, and just showing you sometimes trying to find our neutron number actually does unfortunately get it wrong. Okay. Again, Bohr did a lot of these studies here using, they call them here energy level diagrams. So getting a sense of what these shells here actually look like. Turned out for these shells here, it has energy on this axis. So far, we've been measuring the energy, measuring the shell number here relative to the nucleus here. For some reason, these shells here are quantized. They sort of occur in different steps. Okay, the electrons have to be on particular shells. The electrons can jump up and down these shells and whatnot. One thing that we learned as we looked at developing a new configuration model was these shells here aren't all the same either. So we ended up going from an energy level model, going to an electron configuration model. This is where we end up with our SPDF. We call those subshells. We call those different orbitals there. They are in order. S is lowest energy, then comes P, then D, then F. So only by the time we get to higher and higher shells do we get some of these higher orbits. And we started subdividing some of these main energy levels into these subshells. So, for example, shell number 1 has a 1s subshell. Shell number 2 has a 2s, but being a little bit more energetic, it actually has 3 2p subshells. And going on from there here, shell 3 has a 3s, has a 3p, and even has a 3d. Definitely not to scale for us here, but basically it's trying to subdivide some of these floors for us here and getting us a sense of what's actually happening inside the nucleus. Just like we would actually add electrons to the atom itself, we would be filling in the people into, almost like people arrive at your hotel, you put them into these different rooms depending on sort of how many spots you have on each floor. What we did with the electron configuration was we started adding electrons. Okay, maybe 2 electrons go in the first floor, 2 electrons go in the next floor, and we slowly build up from there. We just off-ball from scratch. Remember, we're not given that hotel diagram, so the best way to do it here is just base it off of our periodic table. So our periodic table here roughly looks like this shape here. We're going to separate our periodic table into 4 main regions. We have our S region, those 2 columns here. We have our P region, which is the last 6 column. We have our D region, which is in the middle, our transition metal section. And then there were actually 2 rows that we actually pulled out of the diagram here. Those 2 rows here are F block, So those elements there are going to be F electrons. And we could actually utilize a combination of the row number and sort of where I am in the periodic table to actually find for us what the configuration is. So just for example's sake here, let's take a look at chromium. Okay, I want to figure out chromium's electron configuration, its sort of roster of where all of its electrons showed up. So chromium is sitting right here. Okay, we're going to start off with what's called the full configuration, meaning I'm going to start off from electron 1 and build up all the way to chromium. So chromium most definitely has passed by where the hydrogen would be sitting. I would have had helium that's right beside it here. This is row number 1. We're in S block. So hydrogen would have been 1s1, 1s2. Chromium definitely has those two, so 1s2 at the very least. Then chromium is going to have lithium's electron. Lithium is now one row lower. Oh, one row down means shell number 2. Lithium would have been 2s1, 2s2 for beryllium. Right? And I slowly work my way over. As I get over to boron, we're still row number 2, but suddenly we enter p block. So after writing a 2s2, we start filling in 2p. Again, chromium has way more electrons than that there. We just go straight through boron, straight over to neon. It fills up those 6 spots for the p orbitals, so 2p6. And then we go over to sodium. So sodium here, back in row number 3. Row number 3, S block, so S1. Magnesium would be S2. It has those ones, 3s2. Chromium would similarly here go through the 3p6. So all the filled shells here we just sort of include there. Down to the potassium calcium row here. Potassium is going to be shell number 4. Back in our S block, so 4s1, 4s2. We're getting really, really close. Chromium is actually 4 elements in to the D block. So where we would have said 3d4, again, Ds are a little bit strange here. Because energy shell 4 ended up splitting up a little bit lower than 3d, we start filling the S's before the Ds. And yet here we get chromium as an exception. For chromium, of its 5d rooms, right now we're suggesting 3d4. Notice that we're just one short of having one person in all the rooms there. Again, this is the extent I can explain it to you. Just like for some reason, having a full shell makes you stable, having a half a shell also makes you stable. So as an exception, what happens to chromium is it promotes this electron up. So actually, this very end is going to be 4s1, and we're actually going to fill up that with 3d5. So plain old chromium here. See if you can utilize this periodic table memory aid here to predict which orbital ends up coming up first. Okay. Especially as we get to some of those lower elements here, doing a full configuration ends up becoming very, very thorough, very, very detailed. So what we can do is we can actually simplify things with a simple configuration, also sometimes called core notation. We're going to use the noble gas to represent the core. Okay. And essentially, with the exception of helium, which we're doing, well, that's just 1s2. It just finished off the first shell there. Most of the noble gases here are down here. They're the 6th element into the p row. We're looking for the last p6. So this one here would have been helium. That closes that shell. There's our 2. The next 8 come in here. That closes shell number 2. That's 8 electrons there. Third shell is an 8 or 18. Well, it depends. In terms of valence electrons, which are your S's and P's, that's your 8. However, there are d electrons here that are actually inner electrons. Spatially speaking, they're actually held really, really tight to the core. And we're actually going to, they belong to shell number 3, but I can't actually draw them on the Bohr model. But technically, there should have been able to be another 10 electrons on shell number 3. What I'm going to do here is I'm going to use the noble gas here. I believe it's argon. Argon is 3 shells down here. Instead of writing out all this beginning bit here, I could say argon. That hides all these 3 inner shells here, and I'll just leave it with, let's say, 4s2, 4s1, and then 3d5, given that it's our exception. Okay, so that would be the core notation for a similar chromium here. And one last thing for this little portion here. So far, I've just been dealing with the configuration for an atom. So if I happen to have all my electrons just off-balling lowest shell first, there's 2 types of charges here. The easier type of charge here is becoming an anion. Now, I know this is a metal. It doesn't normally take on negative charge, but remember, we're in this chapter here where we can artificially add electrons or artificially take away electrons anyways. For anion, we're just going to add to the next low energy shell. So let's say I went from chromium, let's say I became chromium -1. Effectively, what that means is one more person comes to your hotel. Well, as I'm adding them in, well, the lowest energy here was 4s. Maybe I start going argon, where I would have been 4s1, 3d5 at the moment. I'm going to start, for every electron that comes adding in, chromium -1 would be 4s2. Then I get 3d6, 3d7, 3d8 as more and more electrons end up showing up. So anions, I just keep off-balling, I keep building up. For cations, a little bit trickier. Cations involves removing electrons. The idea of removing the very last electron, the least stable one here, is correct, although spatially, because these sublevels here actually may potentially be different orbits, we actually want to pull them off in a very specific order. On the outermost shell, you pull off any P's or S's first. Those are your valence shells. Those are your outermost shells. And then what we're going to do is we're going to then pull off any D's and F's afterwards. These are inner shells. So it may not be the very last electrons. So I was slowly filling in S's and the D's. We had that little exception there. But even though energy level 3D looks like it's going to be higher energy, that was the last electron that I sort of promoted into there, I'm not going to remove that electron first. I don't quite have my 4p's yet. I also can't touch any inner shells. That's represented by that argon there. If I have to, I would take this argon, what would have been a 4s1 and 3d5, and I would actually pull off, okay, I become chromium +1, I lose my 4s1. If I become +2, I now start losing my Ds. I start working into those inner orbitals, 3d4, 3d3, 3d2. Okay. In general, having a half-filled cell does make you stable, but the only times we see the exception is for chromium, making it a D5. We also saw that exception for copper. Copper is just really, really close to the far end here. It would have been a D9 in the same vein here. We're going to promote the one electron up from the 4s up into the 3d10. Okay, and just a very quick overview summary of the periodic table portion inwards into the bonding chapter. So again, there's a reason why we organize a periodic table in this fashion. We saw that a lot of the trends, ionization energy, electronegativity, things like that, a lot of them boil down to something about the size of the atom. Now going down the shells here, it's a little bit more obvious here. Well, if I'm starting up, I'm going to be shell number 1, shell number 2 will be larger, shell number 3 going larger here. The radius does increase going downwards just based on the number of shells. Maybe a little bit less obvious here is going to the right. As I go to the right, I'm looking at elements that have the same number of shells. However, what's happening is every time I skip over to the right, I get an extra proton. So +1 proton, I add another 1 proton, +1 proton. All that's going to happen here is as the center of this gets more and more and more and more and more positive, because I'm still on the same shell, it's not like I gain a new shell and whatnot, but what's going to happen is as the center gets to be more positive, while the nucleus might be increasing in size, this inner core here might be actually getting larger, it ends up pulling the shell in actually tighter. So in that case there, we actually see a notable decrease in size. It actually does shrink notably as you go to the right. So if I just want to summarize that there, based on this as a periodic trend, okay, the reasoning has to do with this attraction here to the nucleus. It's not just, oh, I memorized the side is tiny, but in our case here, we can say the radius decreases. Radii is plural for radius. The radius decreases, the radius drops. As I point upwards here, it's because I have less shells. So I go from having 6 shells to 5 to 4 down to 1. And as I go across, we have a stronger number of protons. There's a stronger pull towards the middle. We're going to use the terminology of Z effective. So it's going to have a stronger, you could just say Z effective. And what that Z effective means is there's stronger nuclear attraction. There's more protons, so it ends up pulling the shell here, ending up going tighter. We base a lot of our trends here based on the size. So we did one trend here on ionization. Ionization was the minimum energy needed to remove an electron, right? Basically, here's my atom, okay? It already had a certain number of electrons. I come in with a pair of tweezers, I grab the outermost, the one that's easiest to pull off, and I start yanking on it, try to get rid of this one here. The ionization energy describes how hard is it to actually pull off this electron. If this attraction is very, very strong to the nucleus, I'm going to pull all the more harder to actually get rid of that electron there. So what's going to happen here is, because my size is actually shrinking, so dramatize that a little bit here, because my size is actually shrinking going down that way there, the further away something is from the nucleus, it's not going to be as strongly attracted as something that's going to be nearby. So in this case here, I'd imagine that we are relatively easy to remove. Easy means low ionization energy. While in this case here, as the atom shrinks, we're going to end up getting harder and harder to remove. So in this case here, it's going to be higher ionization energy. So I just plotted that trend for you here. In terms of ionization energy, the ionization energy actually increases. It gets harder as I go up and to the right, because the nucleus here is not having to hold out as far, it's actually pulling in the shell here tighter. And along that same vein here, we did a trend here called electronegativity. This is what decided whether things were covalent or ionic and whatnot. Electronegativity is this measure of ability to tug of war electrons. So specifically, when I'm looking at two atoms, they're supposed to be sharing electrons. Let's say, for example, chlorine and bonding with another chlorine here. I know it's going to be a covalent bond. It's a non-metal, non-metal. Both of these electrons here have a negative charge here. They are attracted somewhat to the positive centers that these chlorines sort of leave behind. That bond there, or the electronegativity, describes, well, the electrons, are they going to lean one way or lean more the other way here? Well, in this case here, it is just plain old chlorine. Chlorine is sort of tug-of-warring against itself. This time here, there's actually no winner. So you can actually look up this electronegativity. It's a number 3.4. It's on this thing here called the Pauling scale. So don't worry about units for that one there. But more importantly for us here, we're interested in is there a tug-of-war difference? Well, I go big number minus small number. Well, 3.4 minus itself here is just going to be 0. In this case here, the delta En, the tug-of-war difference, is going to be 0. There's no winner. In that case there, we had seen later on, this ends up becoming not just any old covalent compound. This is actually a non-polar version of that compound. We have a bond that doesn't have any leaning, doesn't have any one side more positive, one side more negative, but we have it fairly even. This tug-of-war ability here would similarly depend on the size of the atom. Just like having more protons in the center here pulls on its shell tighter, if I pull on my shells tighter, I'm also going to pull on these electrons tighter as well. So we're going to see one of the smallest atoms that we have are going to be fluorine. The closer we get to fluorine, the more electronegative, the better we are at tug-of-warring. We get to be more of a bully. So specifically, let's say sodium has this electron, and here's fluorine. Because fluorine is actually so electronegative, the first thing that happens is they collide together. They try to share the electron, but because fluorine is so much more electronegative, fluorine actually completely steals this electron from sodium. That's what ends up making sodium having a +1 charge, fluorine having a -1 charge, and that would be our case of actually ionic. So the thing that decides what type of bonding we are is this property of tug-of-warring, is this property of are we even or are we uneven? Again, it comes down to size. As the size shrinks, our tug-of-war ability actually increases. So let me just plot it up here. So we're going to say the electronegativity also increases in this, going up and to the right direction. Okay. So they might just pick out any two elements and might say, oh, who has a bigger radius, who has a smaller radius, who has a higher ionization, who has a lower electronegativity, and you just try to find for yourself here who's better at tug-of-warring. Okay. Last little bit of this chapter here had to do with bonding. So let me just go over some of the main key points here. There was a very clear order that we do for this bonding part. We always started with the Lewis diagram. A Lewis diagram here identifies for us all our valence electrons. So again, our valence electrons are S's and P's. Lewis pictures are a lot more interesting for covalent compounds. Remember, for a proper Lewis diagram, you have to have all the possible dots there. Let's just do one for example here. Say I wanted to draw the molecule SO2. For starters, you could have said, well, let's look at the periodic table. Let's figure out how many valence electrons each has. We have a sulfur that has 6. So I'm going to go single, 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 single. We'll pair up 2 of them. Oxygen in the same column here also has 6. So single, 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 single. Again, don't worry about me sometimes using X's, sometimes using dots. That's just to try to verify for us, well, whose electrons belong to which element. I have another oxygen. Usually it's going to be the least electronegative one in the middle. So we're going to have that there. This is what I call the brute force way of doing it. I know these elements based on the column number. I know how many valence electrons they should have, and I'm going to try to attach them until they satisfy that octet rule. Remember, the octet rule has this notion, everyone likes having a full shell. There's something about like the noble gases, they already have a complete shell. We sometimes call that a closed shell as well, that makes it stable. So I'm going to attach myself until I have a full shell. Usually it is the unpaired electrons that do the bonding. So I can see maybe these collide together here. I can see sulfur sort of making a double bond on this side, but I have a little bit more of a question mark. Well, how does this other oxygen attach to this sulfur here? A little bit of a loss. So what we do instead, trying not to do it the brute force method, we devise a set of rules here. It's based off the same sort of story. So sulfur has 6 valence electrons, oxygen has 6. There's 2 of them times 2. Well, in total, I should have 18 dots total on my diagram. What I'm going to imagine is I'm going to collect the 18 from this molecule, and I'm going to slowly add them to it artificially afterwards. So let's plop the sulfur down in the middle. Let's connect the 2 oxygens just with a single bond. The stick here means 2 electrons. That's a covalent bond. Okay. Now you'll notice that already solves the problem here. I don't know how this bond forms, but following this rules here will get me to the correct diagram. Do keep a tally of how many electrons that we've added so far. We had 18, so I've used 2, 4. Now I'm down to 14. I slowly make my way from outside to inside here. We do need to include all the dots. Technically speaking, I should be going dot, 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 pair, pair, pair. But again, seeing as there's no chemistry in these rules here, we just basically make sure all of them have a full octet. So far I've used 8 to the left, 8 to the right, so I've used 16. I have 2 left. These guys on the outsides are happy. The guy in the middle here isn't quite happy yet because I'm currently only sharing 4 electrons. I'm going to add those 2 extra electrons here. I'm a little bit more happy, but not quite 8 just yet. While I am tempted to just come along and add yet 2 other electrons here, because I don't have those electrons, I can't add these dots here. So as I'm following my rules here, well, if I run out of electrons, what could happen is I could potentially drag one of these lone pairs, these sets of electrons, and drag them in to actually bond with the sulfur. So in that case there, we end up with sulfur having the double bond to the oxygen, sort of matches up what I guessed earlier. Again, I still don't know how the single bond actually forms. Maybe we'll see in a second here. And sulfur should have its lone pair by itself. This is the correct Lewis diagram. We'll just leave it as is. And then we're just going to try to figure out here what probably happened going from this brute force method to my actual diagram. Well, sulfur does only have 1 set of lone pairs. So there's that lone pair there. Oxygen here has 3 lone pairs. So strangely enough, I wouldn't have known this otherwise. Maybe I pair up my unpaired electrons. Maybe I need to pay a little bit of energy to do that, to pair those up. Those electrons don't want to be squeezed together, but we're going to force them together. And then probably what's happened here, although normal covalent bonds have 1 electron from each neighbor, we're going to have sulfur be really generous. Oh, I want to glue to the oxygen. I'm going to donate both of the electrons in the single bond to actually attach to the oxygen there. If you want the fancy name for that bond there, we're going to call that bond a coordinate bond. A coordinate bond or dative bond is special in a way because both electrons came from 1 neighbor. Right? So that there was a Lewis diagram. It's identified all the dots. It's identified all the valence electrons that should be on this diagram. We just went through our rules here to get to the right final picture. Once you have Lewis, you can do a whole sort of other things here. You can do the Vesper. So Vesper only focuses on 1 center at a time. It focuses on how many places are negative around the middle. So sulfur here happens to have 1, 2. The double bond counts as 1 domain. Next time you have a balloon, tie 3 balloons together. All the balloons are going to be fighting for space. They're going to push each other away until we get more so a 3D diagram. Sulfur sort of pointing in this sort of triangular fashion. This would have been what's called trigonoplanar or planar triangular. So we would have been perfectly 360 degrees. I've just chopped up into 3 different pieces of the pie here. Our bond angle should have been 120. And yet here this sulfur molecule happens to have a lone pair. This lone pair here is more diffuse, more spread out. It's a bigger balloon than the other balloons. So what's going to happen is it's going to push any leftover bonds even tighter. Earlier I was expecting it to be 120. Maybe we're down to, I don't know, a bond angle of 117 or so. Molecular geometry wise, I said the molecule was SO2. It's a grouping. I know you're based off this triangular planar shape, but if I were just to describe this bottom portion here, I would give you the molecular geometry, my 3D shape, I would just say we're bent at 117 degrees. Also called angular, also called V-shape there. Okay. You'll always have your Vesper chart with you there, so you can just look up some of the names of these shapes here. And you do just try to figure out the geometry of this, because this is what we need to actually figure out, later on we did polarity, intermolecular force, things like that. We need to figure out how the atoms are spatially arranged to find whether the tug of war is cancel or not. So we'll just finish off with that there. Sulfur and oxygen, who's more electronegative? Well, oxygen is closer to the fluorine, so it's more electronegative. It hogs the electrons. Oxygen is hogging the electrons. I do this dipole. I point towards the winner. Oxygen is hogging the electrons. Even though there are a set of lone pairs here, polarity, we're just going to look at the bond strength itself. Sure, there will be little bits of it. This one's pulling to the right, this one's pulling to the left. There's little bits of it that cancel. But you notice both of these arrows sort of hint at the fact that this side is going to be the winning side. This side is more electronegative. It's hogging the electrons. It becomes kind of negative, where the other side here lacking the electrons, that side becomes kind of positive. We now came up with a molecule. We'll call this polar because it happens to have a positive side as well as a negative side. Okay. So based on your polarity here, being a polar compound, in addition to the London forces, in addition to just background charges, positive attracts negative and whatnot, this one here has access to dipole-dipole. If I had a bunch of these SO2s, there's the SO2 with the dipole. Let's say there's another dipole here. Let's say there's another SO2 with its dipole. Remember, these molecules are just randomly floating in space here. There's no sort of rhyme or reason to them here. But we can call this special type of intermolecular force here. We'll call it a dip-dip or a dipole force. And a dip-dip is the interaction between, well, we had a negative end here. That negative is going to like the positive sides of these other dipoles. And then the negative end of this other molecule here is going to like the positive end here. It essentially is just negative likes positive. It's the in-between attractions that we're going to be referring to as a dipole-dipole. That's what's going to determine our state for us here. If these bonds here are fairly strong, you're going to need to heat us up way more to actually melt us and boil us and separate us and whatnot. But the stronger the intermolecular force, the more I can hold together. So we can actually rank this sort of a medium strength in terms of boiling point. We saw molecules previously that had hydrogen bonding, even stronger than this one here. So things that have hydrogen bonding like water, they tend to stay a liquid longer than things that just have dipole-dipole or just even have London forces. Okay. But in any case, just wanted to give you that quick overview. Keep practicing your problems and let me know if you have any questions. Thanks, guys.